All right, so as you should see, if you're following along in sector, you should be looking at about page 112 or thereabouts. And this is just the continuation from question 35 that we did yesterday. Okay, now, also handy to have in front of you the actual worksheets as well. But the focus for today's lesson, and I'll try and keep it short, sharp and shiny, is polarity of molecules and polarity of bonds. Okay, and I'll explain as much as what I can, as quick as what I can, to get through the topic. All right, now, polar bonds. So, before we did this, if you remember, we went through the section on electronegativity. Remember we did that in the periodic table? And so we have to now remember that all of this depends on an understanding of which elements are electronegative and which ones aren't. Okay, and that's most important. Now, the second thing that we have to think of in terms of a polar bond, and I will just talk about a general example now, is if that is a bond between two atoms, we're just going to call them X and Y, we now just have to apply the rule of electronegativity. All right? And so we've got our periodic table, and within our periodic table, we know that the elements to the right are more electronegative than the elements to the left. So we've got that sort of at our disposal. Okay. On this one, it also gives you, I think, a number for the electronegativity rating somewhere. We've got to look with the key. Yeah, it does. That's the stuff in red. See how it's in red? Electronegativity. It's the value of the electronegativity. Can you see that, guys? And so, for example, like fluorine is 4.0, oxygen 3.5, nitrogen 3, carbon 2.5. Now, those numbers you don't have to use, but they're going to be useful if you're not sure about whether a bond is electronegative or not. Okay, so here it is. If it's X and Y, it's fairly obvious it's two different atoms. And so what that means is I look at my periodic table and I work out, well, which is the most electronegative. Let's assume that X is the most electronegative, okay, in this little worked example. Now, if X is the most electronegative, and I draw it again, what it's saying is that on average, not all the time, but on average, electrons are closer to X in the bonding sense, okay? And so, basically what that means is that if we're sharing a set of electrons, then the electrons are going to be focusing here most of the time compared to what they are around element Y. And so it's not really an even sharing of the electrons. We spoke about sharing in covalent bonds before, but on average, they're closer to element X because it's got a greater electronegativity. Everyone happy with that? Cool? All right. Now, what that means is this will be an example of a polar bond. That means, how do I show it? Well, if this is a structural formula for a molecule, and we'll look at a real one in a minute, we'll work our way through that. So, if this is a structural formula, we now have to use a Greek symbol. We say delta negative. And this is also coming up in the chem sketch work that we'll be starting next term, early next term. So delta negative means it's got a small negative charge. It is not Cl negative. It is not ionic bonding. Okay, so all the stuff that we're doing here, it's all still in the topic. It's all still covalent bonding. As soon as I introduce charges, people think, oh, we're doing ionic bonding. No, we're not. We're doing covalent bonding, but that means a small negative charge. Not because it's got a charge, only because there's more electrons on that side of the bond. Straightforward? Now, if there's more electrons on that side, that means that there's less on this side. If there's less electrons on that side, I can see more of the nucleus. So therefore, that gains a delta positive charge. So we say that's an example of a polar bond. Okay? A polar bond. The one that we'll look at, probably the easiest one, is going to be, we'll look at oxygen and hydrogen, and this is just a picture of part of a molecule. It's not a whole molecule, we're just looking at a single bond. Okay? Now, same thing. So if we would look at oxygen and hydrogen in our periodic table, if you couldn't work out the electronegativity, hydrogen is 3.5, so I'll put it there, 3.5, and the hydrogen is 2.1. Okay, the bigger the number, the greater the electronegativity. So that means, on average, electrons are going to be closer to the oxygen. And so that is an example of a polar bond. That will be delta negative, and that will be delta positive in terms of bonding load. Okay? And I'll go through a whole lot of examples of polar bonds as well in a minute. Alright, now, the next one is a non-polar bond. Okay? Non-polar means that the sharing is even between the two elements. Okay? And I can pick on any non-polar or any combination of elements, and if you're thinking, the only way that can happen is if the elements are exactly the same, non-polar. Okay? That means you've got to have the same electronegativity. So if I pick on, for example, a chlorine bonded to a chlorine, this also happens to be a molecule, by the way, but we're looking at the chlorine-chlorine bond, then the electronegativity for chlorine is 3. That's 3, that's 3, and if you can do your maths, they're both the same. So the pull of electrons in that direction is the same as the attraction of electrons in that direction. So overall, that is a non-polar bond. Okay? So if I were to look at that from the outside world, I just see a block. I don't see any charges at all. There's no net change in the distribution of electrons. The electrons are evenly distributed between the both chlorine atoms. So that's a non-polar bond. Everyone happy with that? And so all these sorts of things that I'll write up now, so these things like oxygen, for example, bonded to oxygen, that's a non-polar bond. Okay? The hydrogen molecule, HH, that's a non-polar bond. If somewhere I've got a structure and it looks like this, okay, carbon bonded to carbon, that would be a non-polar bond. Okay? So wherever I've got elements that are identical bonded, and I'm looking at only that bond, that's a non-polar bond. Happy with that? Okay, so that sort of clarifies it, so that all of these elements are the same, they're all going to be non-polar. Anything outside of that's going to be polar. That's a simple rule of thumb. Okay? However, I always tell you that, and then I say, oh, but there are a few exceptions. Because there is a movement, okay? There's like this graduated line where elements can start off, or let me rephrase that. So the polarity of bonds, there's sort of like a middle ground here. And there is a section in the middle that says partially polar. I'm not going to confuse you with that right now. But there's elements that are almost the same electronegativity. An example of that would be this. Carbon and hydrogen. Okay? Carbon is, what's carbon? 2.5. That's its electronegativity. And hydrogen is 2.1. So there's only a difference of 0.4 in the electronegativity between carbon and hydrogen. So they are really close, right? They're almost the same electronegativity. And so we say that that's actually partially polar. Okay? Partially polar, and we'll talk more about that further down the track. Okay. Polar molecules and non-polar molecules. Now, we are a few lessons behind where we should be, and I've sort of changed the order of things. Really, before we do the molecules and polarity molecules, we should be doing valence shell electron pair repulsion, but I've saved that to next term because that affects the shapes of a molecule. We talked about it in ChemSketch when we optimised. Remember how we did that? And we click on the optimise button and adjust the molecule to the right shape. So, for example, if I've got a water molecule, then a water molecule is not linear. A water molecule is V-shaped because it's got something to do with how electrons are distributed around the centre of oxygen. It's not randomly V-shaped, okay? It's V-shaped for a reason. Just like sulfur trioxide, if you look at it, it's actually 120 degrees. So those oxygen atoms are not closer together there, and they're not closer together there. They're all at 120. Okay? You've got electrons here, here, and here. And if you're thinking, you think, well, that's negative area, that's negative area, that's negative area. And so the furthest apart these electrons can be will be 120 degrees. It also happens to be planar. 120, okay? It's going to be a flat molecule. That's something to do with the valence shell electron pair repulsion. So that determines the shape. Methane, for example, is a tetrahedral shape. Same thing. So you've got carbon, hydrogen, we've got 4 bonds that are equal, and these bonds repel to be as far apart as they possibly can be. And so that's the shape, okay, of methane, tetrahedral, but we haven't gone into that in much detail yet. Alright, polar molecules. I'm going to give you one example of a polar molecule, one example of a non-polar molecule, and I'll try and explain that. Okay, so, let's have a look. What was I using? Orange. So, a polar molecule. Well, we'll look at water because we all should know, for example, that water is a polar molecule. Okay, and now it becomes fairly complicated about how we explain a polar molecule. So you're going to have to watch this really carefully and concentrate. Alright, now, if I were to look at each bond individually, so if I looked at, for example, the OH bond. So the first thing you would do in any structure for any polarity molecule, find all the polar bonds first. You have to do that. And there could be several polar bonds in the structure. This has only got 2 of them. There's an OH there. There's an OH here. So there's a polar bond in this direction, delta negative, that would be delta positive. And there's also a polar bond here, that is delta positive. So we've got 2 polar bonds in a water molecule. Everyone happy with that? Those ones that are here. Okay. Now, who does physics? Yeah. Good, Hayden. So if I ask you what a vector is, what is a vector in physics?
Just a quantity with direction and magnitude.
Excellent. So it's a quantity with direction and magnitude. Okay, so a vector represents the direction of a force, and the size represents how much force it is. So that will be same direction, different magnitude. Okay? Now I'm going to use the same idea to explain how the polarity of a molecule comes about. Okay, so it's force in a direction. Now, this has got a polar bond in that direction. And I'm giving it an arrow, and it corresponds to the same bond, HO. And the length is that much. It's just the same. If I could transpose that over there, it's the same force there. So I've got 2 vector forces, 2 polar bonds, but in different angles. Okay? Got that? Now what I'm going to do is if I look at the molecule from the outside, and I'm now going to add those forces together, not that we're having a physics lesson, but it's still appropriate, I would need to take this, it goes head to tail, so I'm going to move that over to here. I'll move that from there to there, and I end up with a resultant force in that direction when I add these vector forces together.
Yeah, we're doing that in specials.
Good, so you know about vector, excellent, Connor. So adding vectors together helps you to understand why molecules polar. I hope it does anyway, alright? So, force that way, I add them together. So now, the overall polarity of the molecule, if I redraw the molecule, down here, okay, from the outside of the molecule, what that is telling me is that at the top of the molecule, not that it's top or bottom because we know the water can, water's moving around, but depending on how I'm looking at the molecule, wherever I approach the molecule from the top, oxygen side, bottom side, whatever, okay, wherever I approach it from this direction, I am going to see a delta negative. It's going to be electron rich around the oxygen. If I look at it from the bottom, if I look at it from the hydrogen side, doesn't matter which way that is, okay, if I'm looking at the molecule from here, for example, it's going to look positive to me because I'm looking at more of the nucleus than the actual electron cloud. If I look at it from this direction, I'm going to see both. I'm going to see some positive on this side and some negative over near the oxygen, because I know that the polarity is in that direction. Okay? And so that's what we're talking about. So this will be a slightly positive, this is slightly negative, because of the distribution of electrons, because of the difference in electronegativity, because when we add up the vectors, they don't balance. There's an overall net force. Okay? And so from the outside, the molecule will look delta positive, down the bottom, delta negative up the top, but I'm using the word top and bottom, but there isn't. Okay? There's the area that you approach the molecule from. Happy with that? Now, that's a simple molecule, okay? The same idea applies with complex molecules that we'll do later. Okay, now we're going to look at another molecule. We're going to look at carbon dioxide molecule. Now, I've chose that for a purpose because carbon dioxide, shape-wise, again, understanding that we haven't done shapes yet, that is the structure for carbon dioxide. Okay? Alright, so CO2, there's the molecule, or there's the structural formula for carbon dioxide. And it's linear. You don't know why it's linear yet, okay, but I'm just telling you it's a flat molecule, and I've got an example of it here. There it is. Carbon dioxide, that's what it looks like in 3 dimensions, okay? Everyone cool with that? Now, same things apply. So what I'm going to do is, I'll look at each bond individually. So I'm going to look at this one. I'm going to look at the carbon-oxygen bond. And I would tell myself, oh, oxygen is greater electronegativity than carbon. That means, in terms of polarity, that will be delta negative, that will be delta positive. Whoops, delta. Finish it off. Alright? Everyone happy with that? Okay. Same over here. Carbon, oxygen, delta negative. Now I have this. And I'll use my vector idea again. So I've got a force in this direction. There it is. The arrow head tells me that's the negative. And I've also got a force now in this direction. Not very good at drawing, but there you go. Okay? Now, what happens if, from a physical perspective, physics, forces perspective, if I've got two forces in the same direction pulling away from one another, what's the resultant then? Zero. So if I were to add those two vectors together, if I took that one, and then I add that one, they cancel one another. There's no net force. If I had something like this, if I had a force like that, and a force like that, then of course the result would be mainly in that direction. So we're just adding vectors now. However, this is not what we've got. We've got this. So, what does carbon dioxide look like from the outside? Well, let's see it. Carbon dioxide from the outside looks like that. Has it got any charges? Is there any net charges in carbon dioxide? No. There's no partial charges in carbon dioxide at all. And so, hopefully you may be thinking, maybe not, okay, but carbon dioxide is a gas. Does anyone work out why do you think carbon dioxide is a gas at room temperature then? Here's a carbon dioxide molecule. Here's one. Here's another.
Gas.
Why is it a gas? Why is carbon dioxide a gas? Why?
There's just no attraction between molecules.
Perfect. There's nothing that says, why would this carbon dioxide molecule come with this carbon dioxide molecule? Why would they come together? There's no reason. Because these are just floating around in the lab right now as I'm breathing out the carbon dioxide.
Yeah.
I'm not breathing out any liquid, I'm breathing out carbon dioxide gas. So there's no attraction between these molecules. We'll find out later there actually is, okay? But for the purposes of what we're doing now, there's no attraction at all between these molecules. There's no reason for them to come together. That's why carbon dioxide is a gas floating around at room temperature. However, water, so I'll get a beaker full of water, okay? But water is not a gas, not at room temperature. Water has to be contained into a container, as you know. It's a liquid. Oops, got wet hands. So, why do you think that water molecules are a liquid at room temperature? Any ideas? Because they are polar. They attract one another. So we know this is delta negative, don't we? We know that's delta positive. So what they do is this. If they come together like this, no, it's going to flip like that. And now they're going to be able to form some force of attraction. We call that hydrogen bonding. We'll do that again in a few weeks. So all the water molecules have got a polarity. So therefore all the positives and the negatives will attract the opposite charges. So that's why water is held together as a liquid. Okay? So if you are aware of any chemicals that are a liquid, it tells you something about the polarity of the molecules. The more viscous the liquid, the thicker it is, the stronger the force. Okay? But we're not going down that arrow yet. So I'll put the water back in the beaker. So, whoops. Carbon dioxide is a gas because there's no attraction between the molecules. They're nonpolar. We know why they're nonpolar. Water is a liquid. It's a polar molecule because there is attraction between the molecules. Okay? Everyone got that? Okay. Fantastic. We'll leave it at that and we'll take it a little bit further later.